All right, let's just jump right into it. Welcome to this explainer, where we're going to dive really deep into the fascinating and sometimes intimidating world of ergodic theory and see exactly how it translates into rigorous, machine-verifiable code. Now, if you've ever looked at advanced mathematics or formal computer science proofs and felt completely overwhelmed by the sheer amount of jargon, let me tell you, you are absolutely not alone. It can look like an alien language. But today, we're going to strip away all that complex terminology and focus purely on the foundational logic underneath it all. We're going to explore the massive, real-world stakes involved when we move away from basic human assumption, where a programmer just crosses their fingers and hopes a variable stays within its bounds, and move towards absolute, mathematically verifiable truth. We'll uncover how high-level, almost philosophical mathematical concepts are broken down to their simplest possible parts so that a computer can mechanically verify them. Honestly, the contrast between the intimidating jargon and the incredibly simple math we're about to uncover is mind-blowing. So let's get into it. So the document we're analyzing today was generated on May 5th, 2026. It falls squarely under the category of ergodic theory, and it contains 3 distinct, highly complex Lean source files. Now, for those who might not be super familiar, Lean is a functional programming language, but it's also a theorem prover. It's essentially this incredibly powerful tool used by top-tier mathematicians and system architects to digitize math. But what does digitizing math actually mean in this context? Well, it means Lean doesn't just calculate numbers like your standard desktop calculator, it evaluates pure logic. And it does it so rigorously that a computer can mechanically check every single step, ensuring that the proofs are unequivocally 100% correct. This is absolutely crucial because it entirely removes human intuition and, more importantly, human error from the equation. We're going to unpack these specific files to understand what they are genuinely saying behind all that dense code and syntax. Here is our roadmap for today. First, we'll look at translating ergodic code. Second, the mathematics of debt. Third, bounding the void walk. Fourth, quorums and system bridges. And fifth, the real value of these proofs. Okay, starting with section 1, translating ergodic code. Let's start by looking at why on earth we use such complex, almost sci-fi sounding names for these mathematical concepts and what they actually represent when we're talking about a dynamical system. Our first file tackles something called incomplete ergodicity. Now, in physics and really high-level math, ergodicity generally refers to a dynamical system that, given enough time, visits all parts of its space equally. Basically, it's about averages over time perfectly matching averages over space. But the word incomplete implies a system that gets stuck, right? It just can't reach that perfect balance. Our first Lean file models exactly this phenomenon by looking at how a system handles lingering historical debt over multiple cycles. Think of historical debt kind of like that one terrible credit card bill from your college years that you just can't seem to shake. You know the one. Only here, in systems architecture, it means bad data, system errors, or computational backlogs that are just gumming up an entire computer network. If the conditions aren't exactly right, that historical debt never clears, and the system literally never reaches a stable, balanced state. Which brings us right to section 2, the mathematics of debt. Moving into the actual math, let's break down exactly how this historical debt is calculated in the Lean code itself. This specific snippet defines the historical debt function. It looks at 3 specific variables: initial debt, the number of cycles, and the decay rate. And notice how all of these are defined as nat. That simply means natural numbers, 0, 1, 2, 3, and so forth. No fractions, no negatives. The logic here is actually remarkably straightforward once you read it out loud. It's just a basic if-then-else statement. It says, if the decay rate is perfectly 0, then your debt remains exactly what your initial debt was. It doesn't shrink at all. Otherwise, if there is a decay rate, you divide your initial debt by the number of cycles plus 1. Let's walk through a theoretical example just to make it super concrete. Imagine your initial debt is 100. If your decay rate is 0, it stays 100. Cycle after cycle, forever. It's stuck. But if a decay kicks in, cycle 1 divides that 100 by 2. Cycle 2 divides it by 3, and so on. So obviously, the more cycles that pass, the smaller and smaller the debt gets. Now, when I first saw the name of the theorem proving this, perpetual attractor blocker, I've got to admit, it sounded absolutely terrifying. It sounds like a doomsday device pulled straight from a theoretical physics textbook, right? But translating the Lean code reveals something surprisingly simple and honestly, almost funny. The massive contrast between the intimidating terminology and the actual reality is just striking. This theorem mathematically proves that if your initial debt is greater than 0 and your decay rate is strictly 0, your historical debt will always remain greater than 0. That's it. your debt is permanent. It's literally just a formal mathematically verified proof establishing that if a number doesn't decay, it stays the exact same. The perpetual attractor blocker just means your debt isn't going to magically vanish on its own. And this builds beautifully into our next file, which is called Moonshot Conscious Voidwalker Ergodicity. I mean, wow. You really just have to marvel at that name for a second. Why do system architects use such poetic, sweeping names for lines of code? Sometimes it just reflects the sheer ambition of the system being built, but the absolute beauty of formal verification is that no matter how grandiose or philosophical the name is, the mathematical reality underneath it has to be completely objective, completely transparent, and beautifully simple. Let's look at what a conscious voidwalk actually is. All right, section 3, bounding the voidwalk. Let's really unpack this so-called voidwalk and translate its underlying logic into plain, accessible English. The file sets up two core definitions that act as a strict boundary condition for our dynamical system. First, we have voidwalk steps. By slowly reading the lean definition, we can clearly see that for any given number n, the voidwalk steps are simply that number multiplied by itself. It is literally just n squared. That's all it is. Then we have the consciousness limit. This is defined as that exact same n squared, but with n added back to it at the end. So n times n plus n. These two formulas, n squared and n squared plus n, establish a fundamental boundary condition that mathematically prevents a system from just infinitely expanding out into the void. Now, to prove how these boundaries interact, the code relies on this incredibly precise logical command, exact nli _add_right. This right here is the core magic of lean. When the system uses this command, it is calling upon a foundational, unchangeable mathematical library. It's essentially telling the computer, hey, go look at the fundamental, unshakable rules of natural numbers. Find the bedrock rule that dictates a number is always less than or equal to itself plus another positive number, and apply it right here. The computer isn't just thinking about it or making a lucky assumption, it is checking the literal bedrock rules of mathematics to definitively prove the grandly titled voidwalk bounded theorem. And this reveals something absolutely brilliant. The entire voidwalk bounded theorem formally verifies the overwhelmingly obvious truth that a number squared is less than or equal to itself plus a positive number. Think about it. It's so simple. If n is 2, the voidwalk is 4. The consciousness limit is 4 plus 2, which is 6. 4 is less than or equal to 6. Boom. That's the whole grand theorem. It is genuinely baffling how simple the underlying math is compared to the heavy jargon. But here's the thing. In high-level system architecture, locking in this obvious truth is absolutely critical. If a computer doesn't irrevocably lock in this boundary, you risk getting catastrophic memory leaks or total system crashes. It mathematically guarantees the voidwalk never, ever exceeds the limit. Which leads us to a really fascinating question. We have our concepts of debt from the first file, right? And we have these strict mathematical boundaries from the second file. How do these verified, simple truths actually build a complex, functioning piece of system architecture? That is exactly where the bridge comes in. Specifically, the sleep, debt, quorum, ergodicity bridge. Let's see how these truths actively connect to each other. Let's unpack that in section 4, quorums and system bridges. In computer science, a quorum is simply the minimum number of votes or replicas a distributed system needs to perform an operation safely. This is especially important when parts of the network might suddenly fail or drop offline. This code perfectly translates the abstract concept of debt into hard, fast rules for a digital quorum. Based on a positive debt number, it defines the failure budget as the debt minus 1, and it defines the replica count as 2 times the debt. Let's walk through this slowly. Look at the table. If your system debt is 1, your failure budget is 1 minus 1, which is 0. You can afford exactly 0 failures, so you need precisely 2 replicas to be safe. If your debt climbs to 2, well, now you can tolerate 1 failure and you need 4 replicas. If your debt is 3, you can tolerate 2 failures, but you must have 6 replicas. This is classic, textbook distributed systems engineering formalized into completely irrefutable code. To ensure this quorum is mathematically safe no matter what, the file introduces another theorem with a massive name. Positive debt embedding yields strict majority. Again, quite a mouthful, right? But if you strip away the intimidating theorem name, the underlying algebra is incredibly straightforward. It is literally just proving that 2 times the failure budget will always be strictly less than the total replica count. In plain math, 2 times the quantity debt minus 1 is less than 2 times debt. Why does this matter so much? Because a strict functional majority is essential to prevent a distributed system from fracturing into pieces. It mathematically ensures that even if the absolute maximum number of allowed failures occurs, the system still safely maintains a functioning majority. And this brings us to Section 5, the value of proofs. This brings us to perhaps the most important question of this entire explainer. Why on earth do we spend massive amounts of time and computational resources writing complex machine-verifiable proofs for such simple arithmetic? Why do we need a supercomputer to formally prove that n squared is less than n squared plus n? The answer lies in the massive scale and high-stakes complexity of modern technology. We use formal verification tools like Lean to ensure these dynamical systems are mathematically bulletproof. When you are building software that runs global financial networks, or spacecraft navigating the void, or critical power grid infrastructure, human assumption is literally your single biggest vulnerability. A programmer might intuitively assume a variable will never exceed a certain bound, and they might be right 99.99% of the time, but edge cases do happen. And in these high-stakes systems, that 0.01% is catastrophic. By translating abstract ergodic theories into verifiable code, we force the computer to rigorously check every single logical step. Lean completely removes the trust me from programming. We build unbreakable logic bridges, demanding absolute mathematical rigor, which ultimately guarantees stability at the most foundational level possible. To wrap up this explainer, I really want to leave you with a thought to provoke your thinking about the unverified assumptions hiding in the technology we interact with every single day. If systems that manage critical data require a rigorous, machine-checked proof just to confirm something as utterly basic as a number squared is smaller than that same number squared plus itself, it really makes you wonder, doesn't it? How many obvious truths are currently hard-coded into our digital world that are entirely based on human trust, just waiting for the exact right edge case to break them? Think about that the next time you put your total trust in a piece of software. Thank you so much for joining me today, and keep questioning the foundations.